Yeah, so today we have a tutorial on code generation, and that's also why I have a slightly different setup, because we will actually do some code generation during this session, and we will do code generation from state machines. So in the last lecture that we had on Monday, we talked about code generation from state machines in UMPLE, and UMPLE was this graphical this textual representation of state machines. So just a quick reminder, I'm going to open the editor here. This is what we used. This is our editor where we can put in state machines. So on was a state, off was a state, and then we have the event push. And we have a transition here that is defined inside the context of the state on. So this means that the transition goes from the state on when the event push happens to the state off. And yeah, this is basically on the right here a graphical representation. And what we're going to do today is we have a task given to us by our boss, and our boss tells us that the company has basically sold some safety critical robot down here to some customers, but it is not programmed yet, and they want us to avoid programming errors, so kind of manual programming errors. So that is why we should use state machines and generate the code. So there are of course a few reasons, and we discussed why we might use code generation. Also the models might be easier to read than the actual code and easier to check. So this is our task for today. And we will do this actually on a real, well, a very small but kind of real robot. So the kind of system architecture, well, maybe I should first show the robot. So let's see. So you should be able to see now a small robot. And well, it's very simple. It has two wheels that it can power with motors. Then this is just a battery pack. This is a motor controller. This is an ultrasonic distance sensor so that it can check how far things are in the front. And then this chip here, it's not very sharp right now, but this is actually a microcontroller, and this is what controls the robot. So but how are we going to get any state machine code on there? So one option, of course, would be to generate C code and then try to flash the C code directly on the microcontroller. But yeah, to make it, this would require always putting a cable on there and compiling, flashing, and all this. So to make it a little bit more, hopefully easier to maintain, what we're going to do is we're going to have this thing connect to the internet and then have our controller for this robot running kind of in the cloud. Well, today it will be on my laptop, but you could imagine that this also works through the internet, of course. So the setup is that we have this robot. It has this small microcontroller. So this is really just an 80 megahertz CPU. So it's really slow. Probably the computers that maybe your parents had when you were very little were already faster than this. And this is, well, also has a very small amount of RAM. And we are using actually some C code to compile it for this microcontroller. So this is Arduino based. I don't know, some of you might know this, this Arduino framework. And then on our computer, on the server, we will basically have a communication using HTTP, so normal GET requests. It will just look as if somebody calls some website, and the response will not be HTML but JSON. But I guess most of you are familiar with this also from other modules and your previous experience. Inside the HTTP server will basically just a kind of a front end to access a state machine or the generated code of the state machine. And because we have some limited sensors on the actual robot, we will also use some graphical user interface to add some kind of virtual sensors. So yeah, I mean, if you see the robot, it basically only has this distance sensor, and to make it a little bit more interesting, we will add some further some further visual sensors. Okay. The first task will be to create a simple UMPLE state machine for the following behavior here. So initially the robot should go forward, and there is an action that allows the robot to do this. This action would be go. So in our state machine, we would somewhere execute this action go. And then when the robot encounters an obstacle, this will be through the event obstacle. It turns, and it can turn to the action turn until everything is clear, which will be signaled by the event clear, and then it should drive forward again. So yeah, very simple description. We have some events, obstacle and clear, and we have some actions, go and turn, and what we are still kind of missing is we need to decide what kind of states we're going to use. And then of course, how are we going to use the events and the actions on the transitions. So in UMPLE, I'm just repeating the syntax here. The syntax of a transition inside a state, you can put a transition, and then the syntax would be you put the event. So in our case, this could be obstacle or clear. Then the kind of arrow, and then a forward slash, which is usual for state machines to define the actions. And then we put an action in these curly brackets. So you can basically put any kind of Java code here, but we're just going to put the single action that we want to call. So it's either turn or go. And then we need to put a target state. So as a quick reminder, we had this example with the light bulb, and every state machine basically consists of a class, and then the state machine itself. Everything has a body with these curly brackets. Then inside the state machine, we have states. So here we would have the on state, and if the event push is received, we go to the state off. So this was this simple state machine that we had in the lecture. So now what we're going to do is I would ask everyone to open UMPLE. So I'll also maybe put this. I think I can even share this this specific one. So what we'll do is we will try to come up with a state machine that we can use to describe to basically implement what is shown on the slide. This first task of going forward and then turning and stuff like that. So I'll just copy this into the chat. So if you want to, well, it looks really ugly in the chat. If you want to use it as a starting point, we can also then click Save as URL that I just clicked. Then it generates this URL. I'm also going to put that in the chat. And then others can see this. So now if you click on that URL, I think you can see this, this state machine. I'm not 100% sure what happens when you edit it, whether it also changes for me. So if you want to see here on the right side, if you want to see the state machine, you can go to options and then say graph with state, so that it visualizes the state machine. But now we are not really looking for this state machine. We're looking for a state machine that implements this behavior. So maybe use that as a starting point. Now I see we can't click on save URL anymore. So maybe use this URL as a starting point you can use, maybe open just both in a tab so that you can get the example to modify and then a new fresh diagram, where then after you're done with your diagram, you click save as URL, then you post it in the chat, and then we can have a look and look at it together. So here is the description again, and the syntax of the transitions, because here we also have actions, and let's for now just put the actions on the transitions. There are also other ways, but for this example, let's just put them on the transitions. So you have to decide what kind of states you want, and then decide what kind of transitions you need. Of course, I think it's also possible to have self transitions when the target state is simply the name of the state that you're currently in. I think it should work that way. So yeah, maybe I'll give you some minutes to think about this. I mean, there'll only be 2 transitions, right? For the one of the transitions will have as the event clear, the other one will have as the event obstacle, and then the one that has obstacle will have as the action turn, and the one that has clear will have as the action go. Okay, so if you if you have something that looks like a solution or something you would like to discuss, then you can click on this save as URL, and then the URL that appears up here you can post in the chat, and then we can have a look at it together and see whether this state machine is something we can put on our robot. And the goal of this session today is to actually put it on the robot. If you have any questions, just unmute and ask your question. We can also discuss this in the group if you want. So does anybody have any suggestions so far?
Professor, can you show me once again how to initialize the code in cruise.umpl?
How to generate the code, or?
Yeah, how to generate code, or how to like implement the code.
Well, right now we just want to. You can basically start with the example in the Oh, wait, that's the wrong browser. There, I posted this one link in the chat. I'll just post it here. That's the one where we already have a state machine, and I'll just change the options to see graph with state, so to see the state machine. Now what we want is we want to have basically a state machine for our robot, so we're not really interested in the states on and off. What we want the robot to do is maybe something more like well, going forward and turning, right? So we could for example update these states here. The on, we could call it maybe going. The off, we could call it turning, something like that. Now we have a mess because the transitions here went to states that no longer exist. So let's update this. So it's quite, yeah, I mean, like going from state to state, that's quite simple. Now we set that the events that we have in our for our robot, they are actually just obstacle and clear, so we don't have the event push. There's a question in the chat, how do we determine the direction of the turn? We don't, or we don't have to. There is simply an action called turn. The robot will decide which way to turn. We don't tell it which way to turn. We just say turn. And it can turn basically on the spot because it has only these two wheels. Well, not exactly on the spot, but almost on the spot. So we will just say turn. So now we said that if we have these two states now, we said that, well, when is it important to receive the event obstacle? So when we're going, it might be important to receive the event obstacle because then we want to be turning. And when we are turning, we need to know when to stop. So we might want to receive this event clear, right? But now, if we would generate code from that, nothing would really happen because, I mean, we would maybe go between states. But what we're missing is the actual actions to do something. So these actions on the slides, we said one action is go and one action is turn, and then we just need to put it in the right syntax. So if we are turning and we receive clear, then we want to go and go to state going, and then if we are going and there is an obstacle, then we want to turn and go to state turning. So now we can generate code. So because generating code here just gives us the Java code, but we actually want to run this, we will copy this model to Eclipse and then generate code in Eclipse. First, is there any question about this state machine or whether this state machine really does anybody think maybe the state machine doesn't do what we are describing here? I mean, the state machine is extremely simple, right? Just two states, two transitions. Does anybody have questions about this? No? Okay, then we can go to try to actually generate code from this. So here is a project that just has this runner to execute code, and here we have an empty state machine. We need to add the states here. So I'll just take the code that we wrote here and copy this into into my IDE. That's it. If I want to generate code in Eclipse, I need to install the UMPLE plugin. There is an update site for this. There's an update site that I put in the README. You will have access to this code. I'll link this code. You can install this UMPLE code generator from the update site, and it generates the same kind of code as the online code generator does. So when we are in this UMPLE file, we click on this UMPLE icon, and it tells us down here, I think I can't increase the console. I can increase the font size a little bit here. It tells us down here that it generated the target artifact successfully. It didn't complain about anything, so the syntax looks fine. And we then can actually open this bot UMPLE, and this is the generated code. We have the two states going, turning. And when we're in state going, when we receive the event obstacle, we check, are we in state going? If we are in state going, we need to go, like, continue in state turning and do the action turn. So that is this transition here. Event received obstacle, so somebody called obstacle, then we go to state turning and turn. So now I have some additional code written here that takes the sensor readings and based on, let's say, we actually we do some comparison here based on the distance. So we check, where do we check the distance? So we check the distance whether it's less than 20 centimeters, and if it's less than 20 centimeters, then we say, well, there's an obstacle. Otherwise, we say it's clear. So every time the robot requests new instructions, we will check the distance and then tell the robot whether it's clear to go or not. So the robot will make sensor managements. The robot will make sensor measurements using the distance sensor. Then it will ask the server, hey, what do I do now? This is what I measured. What do I do now? And then the server will consult the state machine, and the state machine will tell the robot what to do. So now let's try to load this code on the robot. We should probably start the robot first. We need to power it up. So there's some small power issues. It's not that easy to actually power it up, but should be ready in a second. Okay, so the robot is powered up now. And in this project, we'll just execute the robot runner, which starts the web server, and then we'll see. Yeah, wait, let me. So it actually, yeah, starts going, and then if it finds an obstacle, it starts turning. So it turns. Now always turns left, and you see that it only finds obstacles when when it's really in the range of the sensor. Yeah, okay. So I think we might call this a success, and oh, well, the robot hits the mouse. So we might call this a success and power this robot down. Okay, so what we saw here on the console is the web server that we're running here in this program also tells us the kind of measurements the distance sensor did, and then the output that the state machine or that we produced in the code. So here we can see that if we actually call the if we actually do this action go, then this is something we have implemented in this abstract class. Go will simply send the left motor and the right motor both forward. Stop would put them both stop. Turn now sends the left motor backward and the right motor forward. So that's why this would always turn left. And yeah, that's basically how the implementation of these actions happens. This is in the class AbstractBot, and you see here that we say our state machine relies on an external class AbstractBot that does some of the implementation work, but the main control logic will happen in the state machine. So are there any questions? So somebody asked about the direction of the turn. I mean, this is we do this in the lower level implementation here, where we simply say, well, the turn goes backward and forward with the different wheels. So then that's basically taking care of the direction. We could, if we write here turn left and turn right, then we would have the actions turn left and turn right available in the state machine. But yeah, for now we'll just have a simple turn, and we saw that the robot is a little bit maybe a bit fast and dangerous. So let's see. And it doesn't do anything other than just driving around, right? So let's see if there are ways that we want to extend this. If you have any questions at any point, just let me know. So now we are asked to extend the state machine to support the following. So when the robot is signaled to work, which would be the event do work, it goes into a working state. And when entering the working state, all motors are stopped. And while in the working state, the robot must beep. And then when done working, which is signaled by the event done working, the robot goes forward again. So anybody has any suggestions of how to implement this in our state machine? So it looks like we might want a new state. So if we go back to our editor here, we might want a new state working. And then it says here, when the robot is signaled to work, which is the event do work, it goes to the working state. So we should probably add new transitions. So we get the do work, then we go to the working state, and let's copy this also for turning, so that we whether we are in the going state or the turning state, we'll just go to the working state. And we see it's already updated here, so yeah, that looks quite good. Now here it says when entering the working state, all motors are stopped. And it says when entering the working state. So this might be familiar. We had in state machines something called entry actions. And we said for this one we should stop the motors, so the action to execute would be stop. Okay. And then it says while in the working state, the robot must beep, which is the action beep. And this the whole time while it is in the working state. So how do we get this implemented? So there was stuff like entry action, exit action, and do activities. So here what we want to do is we want to implement a do activity. Yeah, let's just check the syntax. Somewhere the grammar or actions and do activities. I'll just have to quickly entry action or do, and then more code. Okay. So it's just simply a do. So here we have also a do activity, and this should be the action beep. Beep is again implemented in this abstract class above. Let's see, are we done? No, we also could receive the event done working, and then the robot should go forward again. So this done working, of course, this then would only be an event we are listening to in the state working. There's not much need in listening to that in another state. So let's see, from working we should go then to going, but going doesn't have an entry action, so what we actually need to do is we also need to make sure we call the action go again. Okay, now we have this transition back to going. So when working happens, from all the states we leave to working, and when we're done working we go back to this state. Okay, this looks fine. So let's copy this to our code generator and see whether we can generate code, unless anybody has any questions. I'm just going to replace this code here. So this is what we just wrote, and let's see if we can generate code. Okay, looks like we were able to generate code based on what's written on the console. And now we should have new events, for example, do work in the generated bot impl. Bot impl is the class that is generated automatically from the state machine. So yeah, this do work thing really exists, and we see that it checks whether we are in state going or turning, and well, in both cases it goes to the state working. So this all looks quite good. Now we should probably just check what happens. So let's run this thing again. This is actually the graphical user interface, extremely simple, just has two buttons. The do work button, and when we press the do work button, we actually set the flag work to true, which would signal the state machine that we received the event do work. I'll just set it both to false again, and we will start our robot. This was the tricky part. It will probably connect really quick to the Wi-Fi and start going crazy again. Yeah, okay. It's yeah, it's driving again. So now let's go to our, where's our GUI? We want to tell it actually to do work and see. Okay, good. We don't hear a beep. I think there is something wrong with the implementation of beep, but we see that it stops. So what we also should see is once we tell it to stop working, it should be able to go back to the state forward. So let's have a look. I'm going to press this button and yep. Okay, and it's driving forward again, and based on, yeah, let's stop it again. Okay, now we have a way to stop it with working. But yeah. So are there any questions about this this state machine? I'm just going to terminate that again. So were there any questions about this state machine? Here we saw different features like entry actions, do actions, entry actions, do activities, and again the transitions. So if there are no questions, then there is one more.
Excuse me, Professor.
Yes. Yeah.
Is there any chance like can we implement all these actions in a single state machine? Like entry and do entry, do clear and do work in a single state machine?
So here, I mean, the entry action is implemented for the state working, and you can basically do an entry action for every state. So we might, I mean, a thing we might want to do is here we might want to have an entry action that does for the going. We might want to do the go. This way we wouldn't have to write the go on this transition here to going. And then of course we could also remove it here because that's the only cases when we want to do the go is when we are actually entering the state going. I'm not sure if that answers your question. Was your question different or? So you can basically put these entry and do actions in every kind of in every state. Okay. Yeah. Then what we're going to do next is, I mean, yeah, we can of course now do the same for the turning instead of putting the turning on the transition. But yeah, let's just keep it a little bit interesting. Here the action is on the transition, and here the action is the entry action, because then we make sure that we are initially going. I think technically we shouldn't be initially going because we are instead going, but going never executed go. The reason that the robot always starts to drive is because something is probably blocking the distance sensor, and then it goes to turning, and yeah, and then it goes crazy again. Okay, so Let's see the next task. So we now implemented this. We implemented this working or the do work event and the done working event. And now we're going to have a look at the final version. So it's not that we always want the robot to, so the robot might get into tricky or emergency situations. So we also want to implement an emergency stop. And then we should only recover from that emergency stop when the emergency stop is released. So this is a bit different from working, because the working state might have additional things like this do action, but the emergency stop really should be only the emergency stop. So we are going to extend our state machine to include a new emergency stop state. And the way it should work is, in case of an emergency stop, which is signaled by this event, the robot must enter a special emergency state. And then when entering the state, all motors are stopped. So again, we'll have an entry action. And then when the emergency passed, the event release emergency stop appears. And this means the robot should return to the normal operation. So the normal operation is everything other than the emergency stop state. So let's take this updated state machine here, put it in the online editor. So the reason that I'm always going back to the online editor is simply because it's nicer to see it visually. Oh, something happened. Why does it look so much simpler now? The state working doesn't have any outgoing transition. There was something wrong with the syntax here. I removed the actions on the transitions, so then I should have the forward slash. Okay. Okay, good. So now let's see. This is our state machine, and we said we need an emergency state. Okay, now we have the emergency state. And actually, what do we do now? Do we create 3 transitions from each of these states? Or is there something more clever that we could do? Anybody have an idea? I mean, the problem is later, if we extend the state machine except for the emergency, then we will need to remember to copy all the emergency transitions, right? And that's really not nice to maintain. So maybe what we should do is we should use some hierarchical states. So it's quite easy to use a XOR state here in UMPLE. What we do is we make a new state that we call normal operation, and then we basically put everything that we had before except for the emergency into this normal operation. And then we can add a transition for that state. So now if we write here, we are adding a transition for the state normal operation. And there was this event, emergency stop, and we said this should lead to the emergency state. So let's see, do we get that transition? Yeah. Now, this means that whenever this event occurs in any of these states, we will go to the emergency state. And then what it said here, so in case of an emergency, we must enter this emergency state. Okay, that's what we did. And then when entering the emergency state, all motors must be stopped using this action stop. So this would be again an entry action. And then it says when the emergency is passed, with this event release emergency stop, the robot should return to the normal operation. So yeah, now this means basically we have a new transition here, release emergency stop, and this transition would go to the normal operation state. So yeah, this would basically go back here. And the meaning of this is, of course, if we go back into the boundary of the hierarchical state, we go to the initial state of this one. But then if we are blocked, we immediately go back to, well, turning, or if there is work, then we immediately go back to working. So that should be fine. Any questions about this state machine? Should we see if it works? So I'm going to copy this state machine to our IDE. Now it's a little bit larger, but I think it's still fine. We have this emergency state. Okay, so let's see if we can generate code. Looks like code generation worked, and now what we should see in the implementation, so the generated code, we should see these hierarchical states, and yeah, here they are. So the state machine has, on the highest level, has two states, the normal operation and the emergency. And then inside the normal operation, it has going, turning, working, and null. And we said in the last lecture that this null actually means that we are not inside any of the sub-states, and that makes perfect sense because when we are in the emergency state, we are not in any sub-state of normal operation. Okay, now that we have this code generated, we might want to see if it works. So let's run this again. The robot runner, which creates the HTTP server, and then here is our nice graphical user interface where we can just do these two things. So let's go back to the robot. I'm going to start the robot again. Okay, let's see if it, oh yeah, it starts going. Okay, so now let's say there's an emergency and we want to hit the emergency stop. Okay. Good. Yeah, so here down in the console, I'm also printing which state we're currently in. So you see right now we're in the emergency state, and let me just point it upwards so that it shouldn't find any obstacle. Now if I disable the emergency again, it's back in the normal operation going. Now it's in normal operation turning, so I'm printing the current state of the state machine, which UMPLE provides us with. Yeah, and I guess we should do emergency stop. Okay, yeah. Okay, yeah, so now we have basically shown most of the interesting features of state charts, state machines, and also the kind of code generation that we could do. So we have hierarchical states, we have entry actions, we have transitions with actions, we have do activities, and yeah, again, a bunch of more transitions back to boundaries of hierarchical states and things like that. So yeah, this, of course, if you want to do code generation in your own project, what you need to do is you kind of need to write some wrapping code. So this bot impl here is the generated code, and we should never modify it. But the bot impl actually uses the abstract robot, which is a kind of closer to hardware implementation of the events. So here the events that we saw, they are here just placeholders that say, well, this event is not yet implemented, because they will be overwritten in the code generated from the state machine. So if we write here do work, this means that UMPLE will create a method do work, and this will override this do work implementation here. So if we had the very first well, the robot is still running. Okay, if we had the very first implementation here where work and emergency stop were not implemented yet, then I think that we should probably see on the console that it tells us when we press emergency stop. Oh, that's too fast. Yeah, it tells us that emergency stop is not handled yet because it uses still our wrapper, kind of our abstract bot. But then with the latest implementation, we saw that this is overwritten in the code, and the state machine then takes care of it. Okay, so this way you can basically generate or include generated code from state machines in almost any kind of project, and UMPLE is quite a good alternative because it can generate single Java files from state machines that are very easy to integrate into your own code and to use for code generation. And yeah, as you saw, we can basically generate or describe the behavior on this very high level to clearly see what's going on, and then we press a button and we get the code running on devices like this robot. Well, technically it was running on the computer and communicating with the robot, but yeah, that's very, very similar, of course. Okay, are there any questions about the things that we did today? This was the last iteration of this robot. So we did different extensions where we all used different features of the generated code. Does anybody have any questions on state machines or code generation? So I'm going to share all this code. The only thing, if you want to use the code generation within Eclipse, what you will have to do is you will have to install the UMPLE plugin, but I also have this very, very brief README where it tells you how to install the UMPLE plugin. It's really just an update site. But you can, of course, generate the code on the web and then copy it into your bot UMPLE, and that should be the same. So this bot here, this just generates the code for the bot UMPLE, and I have the different versions pre-prepared here. So this is the different iteration steps that we did. So if you want to look back at previous versions that we created and generate code for them, you can do that because they're all here and they all generate into the same file. So this means that you will be able to run the robot based on whatever version code you generate. Well, you actually can't run the robot because that's a physical robot here, but yeah, you can basically put the requests in the browser, and you can also build this robot if you want. I can put the list of parts for this robot somewhere in the README as well. Okay, are there any questions on this? Okay, if there are no questions on this, then that's it with the tutorial for today. We are right on time, just 1 minute remaining, so that's fine. Yeah, if you like to build the robot, I'll just put the parts. I bought some parts of it on Amazon. I think you can get everything on Amazon. It's a bit, yeah, it's a bit more expensive if you buy it on Amazon than if you buy it somewhere in somewhere in China where it then takes a month to get here. But yeah, I'll let you know which parts it has. It doesn't have many parts. You know, it really just has this sensor, this chip here, the microcontroller, this motor driver. There are many alternatives for these motor drivers. I think this is one of the most simple ones because it runs with the same battery power as the microcontroller. So there are other ones which run with higher voltage because the motors need to be stronger. But here, yeah, you see, I already put the motors at something like only 70%, and it's still too fast for this table. In a lecture theater, it's nicer because it can actually drive a bit around. But yeah, on my desk, it's a bit limiting. Okay, yeah, I'll put all this information up. And of course, the code generation stuff you already have. I'll share this project on Blackboard.
Excuse me, Professor.
Yep.
Yeah, can we control speed via state machine generating code?
Yes. So basically, what I mean, I can show you the. You could do that, but what you would need to do is you would need to make the microcontroller code a little bit more complex, because right now the only thing it takes is basically this is the JSON that it produces, that it says the right motor goes forward and the left motor goes forward. So right now it only does forward and backward. And then here I'm just checking the JSON code. This is the code that runs on the C code that runs on the microcontroller. So here I'm just checking whether it's forward, backward, and then I'm setting it to these values here. So you can set these values manually, of course, but then you would have to transmit them in the JSON. So you would have to basically change the code, this code, to read integers instead of just forward and backward. But then what you could do is also you can change it in the state machine, of course, to then instead of just go, you could probably either just assign speeds. That's one way, or you can just transmit some values. I mean, here what really internally happens when this go is called, it actually, the go, let's see, the go is here. It actually just assigns these values, right? So the same way you could assign numbers, and then I think you can put parameters here where you could set the speed, or we could simply, I guess it would also compile if we say left M. This might be private. Let's see, this is private, so we would have to call a setter, like set left M to motor command forward. I think this should be valid code that is generated from it. So let's have a look. Yeah, this is valid code that is generated. So basically, yeah, you can basically integrate Java code here, and then the Java code basically needs to be translated to the right numbers that you then pass on to the microcontroller. So yeah, there's no problem in setting the speed. That's all possible. Okay, any other questions? So basically by integration of Java code into state machines, which is what UMPLE supports, you have a very, very powerful tool. So it's even a bit more powerful than the UML state machines, because in the UML state machines you can't embed code directly, but in this UMPLE version you can.